Here's the text exactly as provided. There's something deeply satisfying about watching a skilled machinist sit down at a manual CNC console and start punching in G-code by hand. No fancy CAD/CAM software, no automated toolpath wizardry. Just a guy, a machine, and decades of hard-earned knowledge. That's what hand programming is all about, and it's still very much alive in machine shops across America. The material being cut here is 12L14 steel, a free machining grade that's been a shop favorite for generations. The L stands for lead, which is added in small amounts to act as a built-in lubricant during cutting. That's why 12L14 machines so cleanly. It breaks chips nicely, it doesn't gall the tool, and it holds tight tolerances without fighting you every step of the way. If you've spent any time at a lathe, you know exactly what we're talking about. Now let's talk numbers, because the numbers here are what make this interesting. The cut depth is set at 0.030 inches. That's about the thickness of a standard sheet of copy paper, times 3. It sounds tiny, but in the world of precision machining, that's a real bite. And the feed rate is running at 0.025 inches per revolution. Meanwhile, the spindle is turning at 800 RPM. Put all that together, and you've got a cutting operation that's methodical, deliberate, and controlled, exactly the way a good machinist wants it. Hand programming means the operator is entering every line of G-code directly at the machine control panel. No importing files from a computer, no pushing a button and walking away. You have to know your speeds, your feeds, your tool offsets, and your coordinate system cold. One wrong number and you've got a crashed tool or a scrapped part. It demands full attention and full accountability. Rough machining is where the real stock removal happens. After this, the part goes back for a finishing pass. Tighter tolerances, lighter cuts, better surface finish. But none of that matters if the rough work isn't done right. Get the rough pass wrong and you've got nothing to finish. Get it right and you've set up the next operation perfectly. Here is the text exactly as provided. Now here's something you don't see every day. Massive steel storage tanks, some of them standing 12 to 18 meters tall, built using a rolling method that seems almost too clever to be true. At Ukrstalkonstruktsiya, they're manufacturing tanks with capacities reaching up to 72,000 cubic meters. To put that in perspective, that's enough to hold tens of millions of gallons of liquid. Here's what makes their process genuinely fascinating. Instead of assembling these massive structures plate by plate on site, which would take enormous cranes, huge labor crews, and weeks of work, they roll the entire tank shell into a coil right at the factory. Think of it like rolling up a sleeping bag, except the sleeping bag is made of structural steel and weighs hundreds of tons. Once the coil arrives at the installation site, it gets unrolled and stood upright, forming the cylindrical shell of the tank almost like magic. It's efficient, it dramatically reduces on-site labor, and it maintains consistent weld quality because most of the work is done under controlled factory conditions. Here is the text exactly as provided. If you've ever wondered what powers some of the world's largest cruise ships' icebreaker, it's something far more sophisticated. And what you're about to see is one of the most impressive pieces of marine engineering ever developed. This is the ABB Azipod, an azimuthing podded propulsion system, and it's a genuine game changer for the maritime industry. ABB Marine's team is assembling one right here on camera, and the level of engineering precision involved is extraordinary. So what exactly is an Azipod? At its core, it's a self-contained electric motor housed in a pod mounted beneath. Some Azipod units weigh over 300 metric tons. Every bearing, every seal, every electrical connection is installed with the understanding that once this unit goes into the water, servicing it is not a simple operation. It has to be right the first time. Here is the text exactly as provided. Let's talk about something that doesn't get nearly enough credit in the manufacturing world: metal recycling. Not the kind where you drop off a bag of aluminum cans at the curb. We're talking about a full-scale, industrial-grade metal recycling operation with equipment that would make any serious engineer stop and stare. What you're looking at is a complete metal scrap recycling plant built around a sequence of purpose-engineered machines that work together to take raw, dirty, mixed metal scrap and turn it into clean, salable aluminum ingots. Every piece of equipment in this line has a specific job, and when it all runs together, it's a beautiful example of industrial process engineering at its finest. It starts at the feed end. The mobile vibratory feeder, rated at 4 metric tons capacity, is the plant's front door. This machine takes raw scrap metal, which can be anything from crushed automotive parts to industrial offcuts, and feeds it into the system at a controlled, consistent rate. The vibratory action does two things at once. It moves the material forward, and it begins to shake loose any dirt, sand, or small non-metallic debris that might have hitched a ride with the scrap. From there, the scrap moves into the heart of the plant, the TR12 tilting rotary furnace. This is a 15 metric ton unit fired by an oxy-fuel combustion system, meaning it burns fuel in an oxygen-enriched atmosphere rather than regular air. The result is a dramatically hotter, more efficient flame that melts aluminum scrap far faster than conventional air-fuel furnaces. Rotary furnaces are particularly well suited for processing mixed and contaminated scrap because the rotation keeps the melt churning, which promotes even temperature distribution and helps burn off surface coatings, paints, and other organic contaminants. The tilting mechanism allows operators to pour the molten metal precisely when the melt is ready, without having to move heavy ladles around the floor. Once the metal is melted, it transfers into the 15 metric ton tilting holding furnace, and this is where refinement happens. Unlike the rotary furnace, which is all about aggressive melting, the holding furnace is about control and quality. This unit features a porous plug gas injection system, a clever technology where inert gas is bubbled up through the melt from ceramic plugs embedded in the furnace floor. Those rising gas bubbles do something important. They stir the liquid metal gently and continuously, which helps homogenize the alloy chemistry and float impurities, called dross, to the surface where they can be skimmed off. The result is a cleaner, more chemically consistent melt ready for casting. The casting operation itself is handled by a 220 mold water-cooled ingot casting machine. The molten aluminum flows in a controlled stream into a series of individual molds arranged in a continuous line. The cooling is indirect, meaning the water never contacts the metal directly, but instead circulates through passages built into the mold bodies, extracting heat quickly and consistently. This controlled cooling rate is important because it determines the grain structure of the solidified metal, which in turn affects the mechanical properties of the finished ingot. Too fast, and you can introduce internal stress. Too slow, and you lose production throughput. The 220 mold configuration gives this plant impressive production capacity while maintaining tight metallurgical control. After casting, The ingots move to what might be the most visually impressive part of the entire line, the robotic automatic ingot stacking system. A robotic arm picks freshly cast ingots off the casting line and stacks them into neat, stable piles, the kind of precise, repetitive work that humans find tedious and robots excel at. But before the ingots get stacked for final handling, they pass through a rapid cooling section that brings their surface temperature down quickly, where I'm in, which prevents the ingots from sticking together in the stack and makes them safe for immediate handling and shipment. Here is the text, exactly as provided. Here's a piece of equipment that doesn't always make the highlight reel, but once you understand what it does and how it does it, you'll never look at a pressure vessel or industrial tank the same way again. This is the Boldrini Ribo 10 flanging machine, an Italian-engineered piece of heavy forming equipment with a very specific and very important job. Flanging, for anyone not steeped in metalworking, is the process of forming a flange, that distinctive lip or rim you see on the edge of metal plates, pipe ends, and vessel heads. Flanges are how you connect pipes to tanks, how you bolt one vessel section to another, how you create a sealing surface that can withstand thousands of pounds of pressure. Get the flange geometry wrong, and you've got a potential leak point in a system that may be carrying corrosive chemicals, high-pressure steam, or flammable gas. There's no room for error. The Boldrini Ribo 10 handles this forming process with a combination of a rotating die and a forming roller. A flat or preformed metal blank, typically a circular plate that will become a vessel head or end cap, is secured and driven to rotate. As it spins, the forming roller applies controlled pressure along the edge, progressively bending and shaping the metal outward to create the flange profile. The machine applies enormous force in a very precise, controlled way, and the result is a clean, dimensionally accurate flange formed without cutting or welding. What makes Boldrini equipment particularly respected in the pressure vessel fabrication industry is the consistency it delivers. Because the forming process is mechanically controlled and repeatable, every flange comes out to the same geometry. Critical when you're manufacturing components that need to mate with standardized fittings and pass pressure certification testing. Steel tube is one of those materials that shows up everywhere in modern construction and manufacturing. Fence posts, structural frames, furniture, automotive components, conveyor systems, and most people have no idea how it's made. Here's your look inside a real ERW tube production line, running the Birlik Makina BTM 240 model, producing galvanized steel tube at 30 by 40 millimeters. ERW stands for electric resistance welding, and the name pretty much tells the story. A flat strip of steel, called a scalp, is fed into the line from a large coil. As it travels through the mill, a series of forming rolls progressively bend it from a flat strip into a tubular shape. By the time it reaches the welding station, the two edges of the strip are pressing against each other under high pressure, and a powerful electrical current is passed through the contact zone. The resistance of the metal to that current generates intense localized heat, enough to fuse the two edges together in a solid, continuous weld seam. No filler metal, no flux, just heat and pressure creating a metallurgical bond. The BTM 240 from Birlik Makina is built for this kind of continuous, high-volume production. The line runs the steel strip through sizing and forming rolls, with tight dimensional control to produce the 30 by 40 millimeter rectangular profile you see in this clip, a standard size used widely in light structural and industrial applications. After welding, the tube passes through a scarfing station that trims the external weld bead flush with the tube surface, then through a series of sizing rolls that bring the final dimensions within specification. The galvanizing, the zinc coating that protects the steel from corrosion, is applied either before the strip enters the mill or in a separate downstream process, giving the finished product that characteristic bright, slightly spangled surface finish. Roller chain is one of those mechanical components that most people never think about, right up until the chain on something breaks. Hengjiu Chain Group is one of the world's major roller chain manufacturers, and their production line is a showcase of precision manufacturing at scale. Every roller chain is built from the same basic components: inner and outer link plates, pins, bushings, and rollers, all manufactured to extremely tight tolerances because chain pitch accuracy directly affects performance, noise, and service life. The production process runs from raw steel wire and strip through progressive stamping, precision machining of pins and bushings, heat treatment for hardness and wear resistance, and final assembly where the components are pressed and riveted together into continuous chain lengths. Every step is tightly controlled because in a roller chain, a tolerance error in any single component compounds through every link in the chain.